So good morning, everybody. It's still morning on the East Coast and early morning on the West Coast. I'd like to introduce Gary to those who don't know him, but we all know him who are here. We've seen Gary, whose background is in electrical engineering, and he's been in the semiconductor industry for 30 years and has been doing all kinds of experiments with magnetism and with the new programs based on the Tetrahelix. So today he will be going over the new discoveries that are coming out of this past year. You've seen some glimpses of it, but you'll see your discovery process, Gary, and some of the exciting discoveries that are now manifesting in your Tetrahelix simulator. This is called Geometric Transformations of the Tetrahelix and its Relationship to Natural Structures. Welcome, everybody, and Gary. Thank you for being here to share this.
Well, thank you, Bonnie. Just let me bring up my screen. All right, so everybody can see that. Yeah, so thank Bonnie has made some contributions to this presentation as well, so I'll be calling upon her for some comment. In fact, she recognized some structures that are sort of emerging from some of these patterns. And if any of you guys notice along the way of this presentation, just send me a chat, of your thoughts on what these may resemble. But yeah, this again, it's a presentation on the geometric transformations of the Tetrahelix and its relationship to natural structures. And we'll be looking at a concept of a Tetrahelix loop transformation that can be described as a self-contained system that uses a toric feedback mechanism. Yeah, let me just run a sample of what this is. Just a couple of highlights of what we'll be covering in the rest of the conversation. But the geometry of the Tetrahelix will be used to constrain the storing and releasing of torque energy within the system that results in this emergent pattern of movement. And these emergent patterns of movement often resemble micro and macro structures found in nature and exhibit cyclic oscillations and transformations of its form. And the three main parameters for each of these unique Tetrahelix-based systems that could be modified in a simulator are basically these three following parameters. There's the Tetrahelix subsequence itself, or the base subsequence. There's the magnitude of the harmonic of the Tetrahelix, or its length, number of times that the subsequence is repeated. And then the twist angle between the elements of the Tetrahelix can be changed and rotated in various ways. And that's the only three parameters that I play with in this simulator. The movement itself is all emergent from the loops that are created in these simulations. And they just often resemble some interesting structures that just sort of, I come across just in the kind of a discovery phase. So actually, so this next slide is actually Bonnie made some of these observations. If you want to add some color to oh, Bonnie, you on mute?
So the observations that that I and Gary have made include structures on the macro scale, the mesoscale, and the microscale. Also, higher dimensional forms are popping up in the midst of these. And so Gary is going to show some of those examples in the midst of how he created what he created. And I think that we have a number of examples, including Emiliania Huxley, my favorite phytoplankton, the Hopf vibrations, which we've been talking about, which is a higher dimensional structure based on the hypersphere. We see it on the microscale with mitosis, and also in the macro scale with plasma in the planetary systems. We also see it in I think it goes down to really the Mobius strip and these odd things that that it represents that we're still discovering on many scales. So that's some of the examples that we'll be showing.
All right, thank you, Bonnie. So now I'm just going to jump down to some of the basics and go through a kind of a step-by-step discovery process, and they will progress to the loop transformations themselves. But generally, there's three main classes of tetrahelix that I work with, and they fall into these categories of a linear tetrahelix, there's a spiral tetrahelix, and then these loop tetrahelix, they twist along a circular path that you'll see. And the loop tetrahelix is the main focus for this presentation. And I define the tetrahelix as a sequence of twist angles that are represented by a sequence of digits, where 0 represents no rotation, 1 is a rotation of 120, and 2 is a rotation of minus 120. So that's the description I use. These are just some examples of linear tetrahelix. The associated subsequence is listed below it that just allow me to reproduce these within the simulator using these sequences. Here are some examples of the spiral tetrahelix and the associated subsequences as well that create these. And this is a sample of some of the loop tetrahelix that they come across. And you'll notice that there's always this gap that results that will never precisely line up for any of these loop tetrahelix. So a summary of what I'll be talking about is we'll be exploring the loop tetrahelix and how it can be transformed into various ways to create these self-contained systems of motion. Now, the illustrations in this presentation are not 3D renderings, but they're based on a physics simulator. In this case, it's the Unity 3D game engine. And it demonstrates the motion of the tetrahelix as its parameters are dynamically modified in the simulator. So we can take the classical tetrahelix, transform that into a dynamic tetrahelix by modifying the twist angle used between its elements. And this causes a dynamic tetrahelix to move along this circular curvature. And the motion of this dynamic loop tetrahelix results in these harmonic relationships between the overlapping elements. And this identifies where torsion loops can be formed by making a connection between the head and tail elements. And in the torsion loops, use the inherent bend and twist of the tetrahelix and ties it into a knot of torsion that creates these emergent patterns of motion. So now I'll just describe the basic rotational connection that I use between the elements of a tetrahelix. And I'll just start with the bend angle, is the angle between adjacent faces of a tetrahedron, or the dihedral angle. And this is considered fixed in these examples. This can be modified as it's currently not supported. The twist angle defines the amount of rotation used at each of the face-to-face connections, and it's perpendicular to the output face that it's connected to. And each new element added to the tetrahelix can be rotated with a step of the twist angle, which defaults to 120 for the classical tetrahelix. So now I can use a sequence of twist angles to define the tetrahelix as a sequence of digits, which I described in the earlier slide. This is just a short video clip to demonstrate the action of these rotational joints. So they're face-to-face connections. They can rotate, they hold the faces together, but have a spring-loaded action that if it's forced to move away from a locked position, it'll spring back to the original position and then oscillate back and forth a bit until it eventually comes to rest. Now, just to give a bit of a visual, these are the three different twist options between any two elements. And I've included the internal arcs to more clearly show the actual structure that's not really visible with using the tetrahedrons themselves. So I define this tetrahedral arc. It's an intersection between a torus and a tetrahedron, where the torus is centered at a midpoint on an edge of the tetrahedron and passes through the center of its adjacent faces. And essentially now this arc still has the essence of a tetrahedron used in the classical tetrahelix. In fact, there's enough information in this arc to reconstruct the tetrahedron itself if you wanted to. So this is just the visual of the different twist options now you'll see when I'm using arcs. And again, unlike the tetrahedron, these arcs create these unique shapes that become more visible, and it allows the internal structure of the tetrahelix to sort of be revealed. You'll notice that these arcs tend to bundle together like fibers and also create these forms similar to vibrations that we'll see in the upcoming slides. So now I'm going to introduce this concept of a dynamic loop tetrahelix. So this is just an example of building a tetrahelix element by element, choosing which way I want to rotate each element. And I'm using a sequence of 1, 1, 2, 2, that this will eventually define a loop tetrahelix. And eventually the head and tail will meet. And this leaves behind that small gap between the head and tail that exists for all of these classical tetrahelixes. Now, for a dynamic tetrahelix, this twist angle step I referred to is actually a variable that I can change inside the simulator. So I'm treating now 1 as a variable with a clockwise direction, and 2 is a counterclockwise rotation counterpart. Now, just to put this in perspective, I've got these 2 vector diagrams at the bottom. Vector diagram 1 is for the classical tetrahelix, and it just shows the relationship between the angles. Here it's a nice clean 120 degrees between all of them. The dynamic tetrahelix interprets this, again, as a variable, not a fixed value. So now when I change the step value in the simulator, it's going to cause some movement, which actually be a little clearer in this animation. So this is just an example of taking the twist angle and increasing it up by 10 degrees at a time. And you notice that the options for clockwise and counterclockwise rotations now converge towards 180. And on the right, you see the corresponding effect of the straightening out or the movement of the tetrahelix through these various angles. This next animation now is just a decreasing angle illustration. I'm using arcs in this case to give more clarity of the overlap as it creates these smaller structures. And in this case, the counterclockwise and clockwise twist options converge towards a 0 degree angle. And in fact, at 0 degrees itself, you notice this whole structure converges down to a tightly packed ring, which will happen to any loop tetrahelix at 0 degrees. And now, just to back up a little bit, just to give a generic example of how you can connect things together in a chain of elements. And this is just an example of a chain of elements connected to have independent rotation with each other, like a combination lock. However, this is not how the simulator makes these connections, which I'll be showing in this next slide. The simulator actually has a connection method where you use an accumulation of rotation for the elements added further along the chain. So if you follow each time one element moves, all the elements to its right take a rotation, with the very last one, doing more rotations than the first one. This may be a little clearer illustration of that, where I've labeled the elements from A through H, going from the oldest to the youngest. I'll use that term. And now for each time an older element moves, all of its descendants move along with it. So if you look at the youngest element H, as its accumulation, it's accumulating more and more rotation. And if to sort of keep track of, in one pass, one frame, there's a geometric progression or a geometric series that sort of comes out. Now, in this case, it's just a simple linear connections. When this is used with a tetrahelix, with a tetrahedral angles, more complexity gets introduced and more geometric series, or maybe a Fibonacci series get introduced, and it, emergent from it. So now I'm going to look at the dynamic tetrahelix and close this gap. So what I'm able to do is, by making a slight modification to the twist angle, the tetrahelix sort of contracts to a point we're at about, in this case, 116.8 degrees is enough of a twist to make the head and tail elements align perfectly at a point which now I can add in a rotational connection to make a torsion loop and close the loop. Now, this is just a similar illustration, but I wanted to illustrate how the two faces between this gap, as I make the twist angle change, you can see it become coplanar. So at this point, they're not coplanar. As I slowly change the twist angle, you'll see eventually they get to a point where they do align. And in fact, they do have a perfect alignment. So when I put a rotational joint in there, it acts like all the other joints. I'll also be illustrating on this little video clip that I can reduce the length. This is a length of 24. I can reduce it by lengths of the bit length. In this case, it's a 4-bit subsequence. So a length of 20, 16, 12, and 8 I'll be looking at. In each of those cases, the gap is much bigger, which means more twisting to close the loop. So now I'm going to rebuild the tetrahelix with 4 less elements, which results in a much bigger gap. I can make the twist angle adjustment, and now I've got the head and tail with a coplanar connection. But you'll notice that all the other connections, their connections are no longer flush, and their vertices become misaligned, although they're still coplanar, because by design the simulator enforces that. And in a few other examples, I'll just, again, rebuild this with 4 less components, much bigger gap, makes a much bigger twist to make those head and tail coplanar. You see more misalignment with the vertices, and in fact, it gets a little even messier to see because of the overlaps involved, which is part of the reason why I migrated over to using arcs to give a little bit more clarity what's going on, inside these structures. So if you took a tetrahelix of a length that's not a multiple of 4, you could never get those head and tails to align properly. So it's restricted to increments of the subsequence bit length. So now I'm going to describe what each of these 3 parameters that I'll be modifying in the simulator. And the first classification is just, the subsequence itself defines whether it's a loop tetrahelix or a spiral or a linear. So this first column would consist of all the potential subsequences that create a loop tetrahelix. I'm going to take one of these and blow it up to introduce the second parameter. And this is sort of the family magnitude. So this is the sequence. Now, this tells me how many times that subsequence is repeated, whether it's repeated 3 times, 4 times, etc. The example I'll be looking at is a magnitude 6, so it's 24 elements. Now I can add in the third parameter, which is the actual twist angle, the unique twist angle, or it results with a fractional harmonic. And these create unique loops that have 1 lap or maybe multiple laps to converge to make a loop. And these D1, D2, D3, and D4 represent the depth or how many laps that's involved in these structures. And the one I got highlighted here allows me to give you a full description of any loop tetrahelix using these 3 parameters of sequence, magnitude, and depth. And I'll be using that to kind of differentiate between the various loops I'm showing. So now in this video, I'm just going to be taking these 4 examples you saw earlier and applying the twist angle changes to go down to these various twist angles that cause these 4 different loops. So I'm scaling down from 120 to about 116.8. That causes the first loop with a single lap around itself. Now I continue to decrease the twist angle, and notice it's actually now doubling up a bit. And when the overlap, again, the overlap is perfect where it looks like 1 single strand, but it's actually 2 loops on top of each other. This is just the third lap being introduced with additional changes to the twist angle. And then the fourth lap gets introduced by scaling it down even further to 33 degrees. And these are the four harmonics for this particular magnitude of this tetrahelix. And now I'm going to introduce the concept of a torsion loop. So we just looked at what I call a dynamic loop tetrahelix. And a torsion loop, they're almost exactly the same thing, except for these following issues or following features. Is the dynamic loop tetrahelix is considered an open loop system where the head and tail elements perfectly align, but there is no rotational connection made between them. The torsion loop is considered a closed loop system where the head and tail elements are perfectly aligned, and there is a rotational connection added between them. Now, both the dynamic loop tetrahelix and the torsion loop allow for its elements to overlap and pass through each other. And you could ask yourself the question, does this non-interaction allow for the creation of stable structures through weaving or other aspects? And you'll see that they do actually make stable structures without the need to interact. They interact amongst themselves, which you'll see. And both the dynamic loop tetrahelix and torsion loop exhibit these harmonic relationships between these overlapping elements, which is just a curious observation. So now this is a little bit more detail on what a torsion loop transformation is. So we can take any one of these loops I identified in the previous video of 1 lap, 2 lap, 3 lap, and 4 lap versions. I put all this data into a table I call an octave table. This is for a magnitude 6 in this example. And you can basically make a loop transformation between any two of these fractional harmonic points to make a torsion loop transformation that exhibits motion, which you'll see in the next couple slides. From a nomenclature perspective, in this fractional column here of 6.1 through 6.4, here I'm using a generic description of m dot d, where m is the magnitude of the harmonic and d is the depth or the number of laps around. Just a way to describe it, classify it. A little bit more on these torsion loop transformations is these torsion loops can dynamically transform their structure between two different fractional harmonics or two different twist angles. So now there's two angles involved. So now we have called 4 parameters in essence that we're changing. Now, to describe the creation of these torsion loop transformations, we start with a dynamic loop tetrahelix, and it's first built with a twist angle that I call the build angle. Then the dynamic loop tetrahelix is put through a ratchet phase by scaling the twist angle to what's called a torsion angle. This is like winding up a spring. It's loading up some torque in the tetrahelix. And then when the torsion loop is closed, the twist angle is set back to the original build angle, and this puts it into the torsion phase. And now the torsion loop will attempt to unwind itself to get back to the build angle, driven by the stored up torque stored in the connection joints. And each torsion loop transformation has a unique movement profile, which is constrained by the structure of the underlying tetrahelix and forms these self-contained systems that uses a torque feedback mechanism, like kind of a knotting. So this will just give you a little bit more of a illustration of a torsion loop transformation between a 1 lap and a 3 lap version of this sequence I showed earlier. And if I'll run this video and show you the ratchet phase. So at this point, I'm just changing the twist angle to twist it to get to that third harmonic. And then now I'm going to make the connection, but it's going to snap back and twist back to the original 1 lap structure. I'll just introduce this concept of a torsion loop transformation equation that might represent the stored energy. And it's just taking these 4 parameters that I have here and applying a product between the number of elements, non-zero rotation elements, multiplied by the distance or the difference or the delta between the two angles, the build angle and the torsion angle, come up with a number. It's just there for reference. And now, again, this is just another generic description to hope that so you understand what's going on in the simulator. Is if you take this section here on the right, it's the first element is the oldest grandfather, and it now is fixed in space and it doesn't move. And the additional elements added rotate, and as each one rotates, its adjacent one goes along for the ride. So there's an acceleration, a kind of mechanical gearing the further you go along the chain. And as soon as this wraps around on a big loop and comes back in from the left, with his youngest grandson spinning at, perhaps 100 times faster than the others, because there's 100 elements it's accumulating motion from. So conceptually, that's what's going on in the simulator when I make this dynamic scaling. Now, to close this gap between, and what I'm doing in the simulator is that I'm removing the stationary connection to the oldest grandfather, so it's not fixed in space no longer. It's actually connected to the output of the youngest grandson that's spinning much faster. And then that's causing a connection, feedback loop between the whole loop. And either the oldest grandfather is going to slow down the youngest grandson, or the youngest grandson is going to try to speed up the oldest grandfather. And then the torque is going to ripple through the loop. And you'll see as it kind of oscillates and causes the motion that we're going to see. So if we apply this now to the simulator, this will just be an example of taking the sequence we saw earlier, but in this case, it has 48 elements in it. So this actually is a two-loop overlapping on each other, or one single strand, but twisted around twice. And now I'm going to sort of ratchet it up and change this twist angle scaling to a point where I make that one bigger loop. And now when I make the connection, it's going to try to get back to the build angle. And in this particular case, it can't unwind any further just because of the structure or the size of this loop. And I will break the loop pretty soon, and you'll see it release the remaining torsion. And it'll actually now start coiling back up to the original position it was in. And this would oscillate for actually, probably several minutes before it actually gets there, but it is heading towards the initial build angle to release all of that torsion. Now this is the same sequence, but now there's 72 elements involved. So this is actually a triple 3-lap loop. And we're doing the same thing by ratcheting up the tetrahelix by changing the twist angle. We get now a much bigger single loop. And now when the head and tail align, I make the torsion loop, and now it does have enough room to kind of reconfigure and unwind, and it slowly starts oscillating, and it'll progress back to getting to that triple loop starting point. You'll see if I'll just speed that up a bit. All right. So there's some oscillation in these joints, so it's springing back and forth, and part of what you're going to see in a number of these simulations, some of them settle down quite quickly. Some of them take several minutes, you'll see, to complete the oscillation. Now, again, I'm just going to actually start adding another concept here of a plot for each of these subsequences. And if you saw the octave table I introduced earlier, one factor is a different octave table for all the different lengths that you could have, depending how many times you repeat the subsequence. And you can take the data. Now, the data is essentially the twist angle is represented on the x-axis, and the harmonic magnitude is up on the y-axis. And each horizontal line here represents the points where the twist angle created a loop with a number of different laps. And the second line is for the 6th magnitude, and then the 7th magnitude is plotted here. Now, this next illustration is just going to show how this data can be built up as I add in data from higher and higher magnitudes. The plot starts revealing some interesting characteristics for the sequence. this wouldn't be available unless you actually started collecting the data. Yeah, so, and now it starts revealing these interesting discontinuities and inflection points that were interesting. I'll just go back to what the end result would be. So for every horizontal line in this plot represents a octave table. But what I can do is along any horizontal line, I can define a torsion loop transformation between any of these 2 points and then see what the associated motion would be. So now I'm going to just introduce a little bit more of a complex sequence. It's a 10-bit sequence of 00111, 00222. There's 250 elements in this tetrahelix. And I use this, say, for a data collection. And I'm just going to scale the twist angle from 180 to 0 degrees. And at 180, it makes a straight linear wave in this case. And as I twist it down to 0, it resolve down to a small ring. And along the way, there's going to be a blue and red disk and a head and tail element. And when they overlap, it represents a potential, harmonic point, or where a torsion loop could be created. It's going by quite fast, but you'll see every once in a while these arcs line up. And for this particular sequence, there's actually 39 harmonic points or opportunities where a torsion loop could be created. Now, in this state, it's a dynamic loop tetrahelix because the head and tail aren't connected, so it's free to move. And it's just moving along this contained spherical, or it's a curvature, until you saw it actually broke the loop there, which will show up in the plot. Now it's slowly going heads towards 0, and I've now have enough data that I can actually go and create a plot for this particular subsequence. And this just includes magnitudes from 2 up through about 63. There's probably about 3,000 data points here, I believe. But there's some interesting inflection points here at certain angles. In fact, this angle down here around 19 degrees, it's sort of a hyperbolic asymptote here that it never quite can get to. So I wanted to see what a torsion loop transformation would look like between some of these points. And I picked this little gap here to traverse, indicated by this red arrow. And that's going to be illustrated in this example here. Now, again, this is just demonstrating the ratchet phase. So I'm just slowly changing the twist angle from 95.9 to about 128.5. And at this point, I'm just about to close the loop and put it into the torsion phase, and see it's going to transform its structure. So now it's going through a little bit more complicated structure transformation. It resolved itself fairly quickly. It'll settle down in probably less than a minute. There is still some internal torque held up in this structure that just gets contained for the time being. Now, if I go back to that plot I just showed you, I was curious about what happened on this area here, this gap. So I just picked 2 different twist angles to traverse this gap. And now that next video is going to run for, I believe, about 3 minutes. So it's a longer video that plays out over 3-minute time frame. And there's going to be a number of structures that, again, this is what Bonnie talked about earlier. And for this particular video, there's 3 particular subsequences, sort of patterns that Bonnie had pointed out that, well, in this particular simulation, there's this Fibonacci spiral pattern in these disc florets of a sunflower that you'll notice early on in the video. This structure reveals itself. A little bit more than halfway through the video, you're going to see something similar, not exactly like a hop vibration, but you'll see some of these similar type patterns evolve. In fact, let me just play a short little video clip here of explaining what these hop vibrations are.
The simplest definition of a hop vibration. It's just a map from a hypersphere in 4D onto a sphere in 3D. How is it mapped? A sphere is fully covered by points. Each point is mapped to a circle from the hypersphere. These circles are the fibers that compose the hypersphere. We'll unpack this in a bit, but first we need to briefly cover the concept of stereographic projection.
All right, let me get back to the slideshow. So yeah, there's more on that if you want to refer to full YouTube. We can make that available. And then towards the end of this video clip, you're going to see what one can interpret as these sphere eversions. In fact, there's more in surface is the halfway point between a sphere trying to turn itself inside out. Now, so let me just run this video. This is, yeah, just over 3 minutes long. Actually, I'm going to run this in slideshow mode to include the music track. Yeah, so in that video sequence again, the hands are off the wheel, and this, the simulator is just directing, where the arc should be moving based on how they're connected and the torque built up. This is another little video clip of what someone, you can maybe visualize this as a spherically eversion as it's trying to unwind itself. So I'll just actually let me play this with the music track as well. So now we're going to move on to, again, this is another structure. Maybe Bonnie, if you could say a few words here. I know you've got a lot of experience with this structure.
Body's having computer trouble.
Oh, okay. Yeah, this is a Amelia Huxley, if I pronounce that correctly, structure made of these coccoliths, abundant phytoplankton, I believe. Again, here's just another sort of comparison between a couple of these screenshots you'll see. Now, and this will be showing up in the next slide. This next video, again, it's only about a minute and a half, but starts with a slow start, but it'll actually build into some animation. So that was, there is actually one more video of a similar type structure. It's a different animation. Again, this takes a little bit of a slow start, but it does start to move. So now I'll jump into another class of structures. So it's this mitosis of the cell division process with these microtubular spindles that happen during the metaphase of this mitosis. And you'll just notice a separation here that some of the other videos may have similar characteristics. Here are some of the various stages, and particularly towards the end here, you'll see some of the structure similar that you'll be seeing in the following video. And then just some interesting geometries here between this 9 sets of 3 microtubules that come together to form this helical structure. So this is not readily available, but you'll see the overall structure of this next simulation exhibits some of that behavior here, just ironically. Go through the same slideshow. Yeah, so it's going a little bit more. I gotta start the video. I slowed it down. This is actually half speed, just to show more detail as it's making this this ratchet phase. So right now it's just being transformed with a twist angle change. The torsion loop hasn't been formed yet. And when I get to this final little change there, now we're going to go into the torsion phase, and now it just sort of just oscillating and almost trying to separate into 2 spherical lobes. It wouldn't take much of a change to the simulator to identify at what point you can make an easy cut and rejoin to actually have these 2 things separate into 2 distinct spheres. But just the hint of that structure was interesting, we observed. Now let me go back to the presentation. Here is another thing that Bonnie has sort of pointed out, that some of these toys, these flow ring spinners, has some similar characteristics. These other video clip I'll be showing you. It also resembles, some of the plasma torus found on Jupiter's moon Io, and these magnetic field lines just have a similar correspondence to some of these shapes. Oh, and yeah, this is just a short little video clip to show this particular structure. This is not going through a torsion loop transformation. This is just a different viewing angles to look at this particular structure. Just this particular sequence coming up with this unique pattern of arcs. I think I do introduce a little bit of torsion. I'm just jolting the structure a bit to give it, you can see it actually holds its structure together. Now, on a similar type group of structures, there's all these other nested toruses that, some of these fractal toruses and these other toys have similar behavior. And this is just a short series of little examples of some of these other nested structures that are created with these other different subsequences I played around with. These were mostly found just by using sort of a random number generator to create some of these sequences and allow me to take a look about what they actually would look like. So yeah, just a sample of some of the ones I thought were interesting. So now I'm just going to introduce a little bit of a element change. So in addition to these arcs, you can introduce any different model into this as a visual. And here I'm just introducing a structure similar to a caltrop. I guess on the right here is a kind of a caltrop, maybe it's a dual of a caltrop because it's connected to the center of the faces, not the vertices. But I think the angles would be identical. And then this element on the left here, I've just got half a caltrop to identify the bend angle between 2 of the faces where the arcs were. And then the little white sphere in the center is the center of the tetrahedron. And that shows some interesting behavior when I'm going to do a side-by-side comparison of one video I showed you earlier. And beside it will be this green and white model. And you can just see how much more detail you can see just by making a model change. Again, Bonnie just highlighted some fact that this Cal Shop design has been around since antiquity. Fuller's meatball has similar structures, and methane molecule has this structure as well. And then again, towards the end of this video, with this new model with the green and white color, you might see some Morbius strip sort of behavior. In fact, it looks more like you'll see a snapshot of this green model, similar to what this origami demonstrates, this Mobius strip behavior. And then one other thing that I just wanted to point out is that a lot of these structures make these torus-based structures, right? So they're not exactly the shape, but they do have that donut-shaped surface. And you'll notice that with the green and white model, you might see the circulation of how this is unwinding, coming from the center and flowing up and around. I thought was interesting. But yeah, let me just kick off this video. It's, I think, about 3 minutes long. No, 4 minutes long. This actually continues on for actually another 10 or 20 minutes. I let it run out, but you get the idea. And only got a few more to show you, a demonstration. This I decided at the last minute. This goes through this transformation of what looks, has a kind of an octahedral shape to it. And as I put it into the torsion phase, it's just going to pulsate between various shapes, but always resolve around this particular structure. Set that up. And then before we wrap up, just a little sample, the same simulator, I've got it ported into a Oculus Quest 2 version for the simulator. And this just, slideshow gives you an idea what it looked like playing it from Oculus Quest. Kind of a crude interface, but you can just use this raycasters to click the buttons. You can explore inside these structures. At some point, I'd like to support a multi-user environment where multiple people can share the same metaspace and metaverse. Just going to come back to the control panel and make a bit of a torsion ratchet face. I just ratchet it up, close it. In this case, all the torque is still wound up in the structure. It looks at this point it's not moving, but there's a lot of torsion loaded up in the structure. Now I can go back. I'm just going to break the loop and let it sort of return back to the original build angle, and go inside and inspect it from a internal inside the structure. And then just a little thought for his wrap up about what can one benefit from this Tetrahelix simulator. Well, design scientists, biologists, physicists, nanotechnologists may have a use for this. Again, it's an experimental tool. Could use for any kind of structural research and collaboration. discovery process. Some of the classification I've done, I'd like to start a cloud-based blockchain database to capture, complete sets of this data to see, kind of catalog what they look like. And then some of the future directions of making this open source to various other initiatives. Again, a fully immersed, VR environment, and ideally a multiplayer environment to do the research. And now I guess we can just open it up for discussion. Let me just check if there's any outstanding questions here. Yeah, so I'm not sure how the resolution turned out.